discuss a very important parameter in classical mechanics is Lagrangian. We denote it by L, which is equals to kinetic energy minus potential energy. The very important in the questions come in the net JRF or any other exams like GATE. Any system will be given and we have to first find the kinetic energy and potential energy and then the Lagrangian and then the equation of motion. So first of all we just find out the kinetic energy expression, which is simply half m x dot square y dot square plus z dot square. We first we have to find the coordinates of the object at that point, means it's x, y and z, and then take the derivative and then square and then add. We will get the kinetic energy expression in Cartesian coordinates. If we consider the spherical coordinates, then first of all convert x into r theta phi and y r theta phi and z r theta phi, and then take the derivative and then square and add. Okay. Similarly for cylindrical coordinates. And then potential energy, how can we find out? Potential energy, first take the reference point and then take the height of that object from the reference point. If let's say this is the reference point and the object lies here, then take this height h or any other parameter, then potential energy will be mgh. And then here plus minus sign also will be there if the object lies below the reference point, then take negative sign here. If it lies above the object reference point, take positive sign. And some other potential energy we can say for the spring, like spring half k x dot square. Here x is not the same here. X is the stretch in the spring, or we can say the s, stretch or compression in the spring. So here both the potential energy will be there if there is spring just like there. In that case both the potential energy will be there. Okay, then Lagrangian will be clear. Okay, then next, what is the equation of motion for that? Let's say we have only one parameter, one variable x dot square plus minus v of x. Okay, the equation of motion will be del L by del x minus t by dt of del L upon del x dot equal to 0. This is a standard equation of motion. We can prove easily by using the action variable. Action, what is action? L dt. What is L? Lagrangian. It depends on x dot and t. Let us prove it simply in 4 to 5 steps. For s to be extremum, delta s will be 0. Extremum means minimum or maximum, we have to find that. Then this is equal to delta L dt. I just take delta into integral to L because dt is arbitrary here. And what is delta L? Delta L, I will use the chain rule here. Delta L upon delta x. Similarly here and similarly here also. If I consider that L is not explicitly depend on t, that is, if in the expression of L there is no t like term, Okay, means in the expression of L there is no t and t square cos t, any function of t, there is no present there, then delta L upon delta t will be 0. Then the action will be delta S will be 0 equal to, put the values of delta L here by putting delta L upon delta t 0. I got this, and this the variable dt. Okay, now I have to separate this. Let's say d by dt of del L upon del x to delta x. What will be it? First derivative with first derivative of this with respect to t, and then this d by dt of this is remain same plus me delta L delta x dot d by dt of delta x, and I can write here dx upon dt, because delta or d by dt both are differentiation and we can interchange both. Then this quantity will be delta x dot. So here this terms will be since this is the perfect differential, if we take integration on this, and we know that delta L upon delta x to del x with boundaries will be 0, then from this equation you can take you can put the value of this from here. Sorry, its value will be 0. So this is the perfect differential. Delta x is outside from the derivative here. Okay, this term will be 0 and this term will dominate here. Then put the value of this into equation. This 0 equals delta L upon delta x plus me, you can write first d by dt, so delta x here minus this term d by dt and dt also, integration to boundary conditions. Then this term will be 0 and the remaining term I can write here d by dt delta x will be common in both the cases and dt. Since these are the arbitrary and we can directly put this quantity to 0, so this is our equation of motion for Lagrangian. Similar cases arises for the case if we have to find just like that we have given a path in xy coordinates. Let's say this is the path here a to b, then we have to find the minimum path between a to b. For minimum path a to b, this will be a straight line, we have to prove that. Then let's say this small element here ds, what is ds here, dx square plus dy square here, then the path will be ds and dx square plus dy square. Let's say dx in common in this, then it will be 1 plus y dot dx. Here y dot is dy by dx. Okay, the our function will be this. Means just like we did in case of Lagrangian, a function f x y y dot will be square root of 1 plus y dot. Okay, just like the Lagrangian. Then equation of motion will be here, delta f upon में delta y minus dy dx here, del f upon में delta y dot equal to 0. Okay, since this function does not depend on x, similarly the case delta l upon delta t is 0. I have put it in case of Lagrangian. Similarly here 0, and after that we get the same equation of motion here. Then the this here, this is what, since f does not depend on y also, and this will be 0. This implies delta f upon delta y dot will be a constant, and we put it, let's say k. And what is that? Differentiate it with respect to y dot, we will get, sorry, y dot square here, and the square y dot square here. So here what is that? 1 upon 2 1 plus y dot square 2y dot equals to k. Okay, then simplify it. Y dot equals to k 1 plus y dot square, squaring both side, k square 1 plus y dot square, and y dot square equals to, sorry, common 1 minus k square y dot square equal to k square upon 1 minus k square. Let's name variable k dot, and square rooting both side, y dot will be k prime, let's say new variable a, and then y dot will be y dot dy by dx, integrating with respect to x, y will be ax plus b, new constant b. So here we get that the path we considered here, a to b, to be minimum if this is a straight line path. Okay, so next parameter, important parameter, is the momentum. Let's say I'm first writing the equation of motion of Lagrangian, delta L upon me delta x dy dt of, okay, if this parameter is 0, then this parameter will be a constant, and what we call it is momentum, sorry, a constant momentum. So we can say that if Lagrangian is explicitly does not depend on that variable, then its momentum will be conserved here. Conserved, or we can say constant. Okay. Next important parameter is Hamiltonian. Hamiltonian is what? Hamiltonian is total energy operator, we can say, and its value will be pi qi dot minus Lagrangian. Let's say we have given a Lagrangian which depend on qi dot t, then Hamiltonian will be pi qi and dependent. Okay, Hamiltonian should be right in these parameters and Lagrangian should be here. Qi is the positions and variables we can say. In our last case I have taken the x2. Okay, so I am considering the generalized case. And what is Qi dot? Qi dot will be find out by that expression equation of motion from here. We can find out the Qi dot if we given, or in terms of momentum will be given just like that, pi equals to delta L upon delta Qi dot. If we take the derivative of L with respect to Qi dot, we will find that pi. This will becomes in terms of Qi. Okay, of Qi dot. Okay, then the next thing we should consider that if given Lagrangian, how can we convert into Hamiltonian, or the relation between Lagrangian and Hamiltonian things. We have to find that. How can we find that? Let's say take the differentiation both sides. First, let's say h we have considered h depends on pi, qi and t, and I am writing its perfect differentiation is by the chain rule. Pi delta h on delta qi in that equation. I also take the perfect differentiation and compare the both sides. Let's say remove the solution, and I'm just writing in terms of pi and qi dot dh will be from that equation pi dqi dot plus में qi dot dpi minus, put the chain rule and Lagrangian here. What is that? Delta L upon my del. We will place this value of dl here. Delta L upon my delta qi dqi, delta L upon my delta qi dot dqi dot minus of delta L and dt. Okay, and ds will be this. Compare the both sides, then what will we get? This qi dot will be delta h upon my delta pi. Okay, and the next thing is in this there is no term of qi dot here. Sorry, this is qi, not qi dot, because the Hamiltonian does not depend on qi dot. So here in this side there is no qi dot, so we will put 0 and pi this term, and the next term will be this minus, as I have already told in earlier, pi will be delta L upon delta qi dot. Okay, and the next thing, compare the time dependent part. Delta h upon delta t will be minus of delta L upon delta t. Then these three equations are will be helpful, and of thing also qi, we will compare the coordinates of qi in this, and the next equation will be delta h upon delta qi minus of, okay, from here will be pi dot, sorry, pi. So here something will be wrong. So here this is not there. This is the case, not qi dot here. So I'll write it minus delta L delta qi. And from the Lagrangian equation of motion, this will be, what is that? What is that? Minus of dy dt delta L delta qi dot. And what is delta L upon delta qi dot? Pi. Then this will be pi 2. So Hamiltonian equation of motion are, there are two equations of motion. Hamiltonian equation of motion are qi dot equal to delta h upon delta pi, and pi dot will be minus delta h upon delta qi. Okay. If our Hamiltonian does not depend explicitly on t, then delta h will be, delta h upon delta t will be 0. It means that our Hamiltonian is conserved, means our total energy will be conserved here. And this will hold if Lagrangian also does not depend on t. If h contains terms like t, then delta h upon delta t will be non-zero, and we can say h total energy will be not be conserved there. Okay. Now I should discuss how to convert Lagrangian into Hamiltonian, or Hamiltonian into Lagrangian. Let's say first I am discussing the topic that we have Lagrangian given. Find Hamiltonian is the most important questions. They will always come in the NET exams or GATE exams. In 2018 also in GATE exam it comes there. 2019 also, 2018 also. Okay. Let's discuss it. And Hamiltonian, we know that Hamiltonian, what is that? P q dot minus L. If L is given, that means L variables are q dot and t will be given there. Means L in terms of these parameters will be given there. Then what is P there? Delta L upon delta q dot. And first find out the P from there. Okay, then put in this equation. Then that's simplifying it, and later on we should convert q dot into P back. Let's say, and similarly first I will discuss if Hamiltonian will be given, how to find out Lagrangian there. And Lagrangian will be P q dot minus h. Then from here q dot will be delta H upon में delta P. Here Hamiltonian will be given in terms of P, Q and T. Then we can find out this, and we can find out this, and then here this will become in terms of P, and later on put P in terms of Q dot and we will find the Lagrangian. Let's take the example. If given, I have an example. Let's say Hamiltonian will be given P square Q square. We have to find out its Lagrangian. What is Hamiltonian? P Q dot minus L. Our reverse is Lagrangian will be. So our Hamiltonian will be given. Then delta H upon delta P we can calculate it. It will be 2P Q square. What will it be? Delta H upon delta P, Hamiltonian equation of motion, Q dot. Put it in this equation. Lagrangian will be Q dot P 2P Q square minus value of Hamiltonian P square Q square. Then what will you get? 2P square Q square will be same as that of P square Q square. And the Lagrangian will be same. Then put the value of P, because we have to find Lagrangian in terms of Q dot and T. Okay. Then put the value of P from this equation, and P will be Q dot square upon 2Q square. Then put here value. What will be? P square है Q dot power 4 divided by 4Q power 4 Q square, and value will be Q dot power 4 divided by 4Q square. This is the Lagrangian. Okay. Similarly, if Lagrangian is given, we can find out the Hamiltonian. Okay. Now I will discuss on phase space trajectories in classical mechanics. How we'll find out the phase space. Phase space means a plot between momentum and its variable position coordinate. P versus Q plot is known as phase space. Means we have to find the relation between P and Q. For this we will use, let's say we have given example in last time we used this example, H is equal to P square Q square. Okay, and then we have to find the relation between P and Q. Then use the equation of motion. What is equation of motion? And equation of motions are P dot equals to minus of delta H upon delta Q, and Q dot equals to delta H upon delta P. We will find both these quantities, and P dot will be partial differentiate it with respect to Q. We will get 2P square Q, and Q dot will be 2P Q square. Okay. What is P dot? Means dP by dt, and here what is Q dot? dQ upon dt. Divided both the things, dP by dt upon dQ by dt. dt will be cancelled out, and we will get 2P square Q divided by this thing, 2P Q square. What will we get? P n by Q. So here just take the p in this side and q and dq this side, and will be minus dp upon p equals to dq upon q. Integrate both the sides. What will we get? This will be log of p and log of q plus some constants. We will ignore that constants also. Then if we take this into side, then log of pq equals to constant, and we can say that pq is also constant and p is inversely proportional to q. It means the phase space diagram will be inversely proportional. Okay, so whenever we have to find the phase space diagram, use the equation of motion. If Hamiltonian does not given, find first Hamiltonian, then use the equation of motion, then just simplify it, either divide by both the equations or put one of the parameter into second one. We will get the phase space. Also, we can find out the individual p or q from these two equations in terms of time. How can we find out? Let's say q dot equals to, we know that we derive it to p q square. Okay, and we know that p is inversely proportional to q. Let's say c is our constant, then put here value of p, c by q, then cq. This is the linear differential equation, or we can do it by simply dq upon q, 2c dt, just integrate both sides, log of q, 2c, c is constant plus some other constant, we get this exponential of 2ct, some variable, some constant here also. So we get q in terms of time. Similarly, we get p in terms of time, just reversing it and multiply with the c. Okay.